first talk, Isabella. The stage is yours.
Okay, so thank you, Eleonora, for your presentation. I'm Isabella, and today I will present to you the topic of my research. But before that, I want to present myself. I'm a second-year PhD student in information technology here at NextLab. But despite this, I have a bioengineering background since I've got my master's degree in bioengineering at both Politecnico and University of Illinois at Chicago. It is for these reasons that my research focuses on computer vision, mainly applied to medical scenario. So to get a little more into detail, my PhD revolves around designing a framework specialized to analyze medical images during end-to-end image-guided biopsy procedures, implementing deep learning method at the algorithmic level to aid the end user with more accurate and faster analysis. So given the complex application scenario, I will start introducing you to the world of biopsy procedures. So they are multi-step, multimodal, and multiscale medical procedures that starts from the acquisition of images of a disease or healthy organ from a patient of interest. And then it proceeds by aligning them to a common reference frame through the image registration step. At this point, the procedure steps into the microscale, where images of the acquired tissue samples are acquired and then analyzed through several image processing techniques to allow the end user, such as physicians or researcher, to produce a medical report. So it is evident that being able to accurately and precisely analyze those images produced could ease the end user to produce a possible diagnosis. Despite this, the current bottleneck in the clinical practice lies in the time-consuming nature of data acquisition and analysis. In fact, due to the massive amount of images that are produced every day in the medical scenario, the manual annotation and analysis have become unavailable within reasonable timeframes. This aspect worsen even further when considering that those images could be of different dimensionality scales or acquired with different modalities and always at different medical centers. So I want to say about 15 years ago, deep learning came around to solve all these issues. In fact, has been demonstrated to be capable of handling huge amount of heterogeneous data at once. In addition, it has demonstrated to ease human error-prone tasks with higher image quality analysis. And furthermore, it has also guaranteed faster analysis thanks to its efficient inference step. So it is for these reasons that I decided during my PhD to exploit the deep learning potentialities while building upon its weaknesses to produce a complete image analysis pipeline for a biopsy procedure. In particular, my pipeline starts at the macro scale with the image registration step and then goes down into the micro scale through several image processing steps. But the key aspect of this work is to focus on the multimodal and multiscale integration of the image analysis. In particular, different modalities of images will be integrating at both the macro scale and micro scale, while different dimensionality scale of the images will be integrated at the end of the pipeline to close the pipeline and ultimately allow the end user to ease from a complete analysis. So during my PhD, I decided to follow a top-down approach, starting from the macro scale with image registration step. As explained by Eleonora, in this work, we try to get rid of the rigid pre-registration step that usually follow the deformable image registration procedure. In particular, during this step, we design a spatial regularization strategy to fix the translational and rotational deformation components that usually are residual from a rigid or affine pre-registration step. We designed this strategy as a loss function that could also be used with a different neural network architecture and allow our network to learn different ranges of image deformation. We tested our strategy on a unit architecture, and we demonstrate that we are able to reach up to 12% of mean structural similarity index measure over the baselines while getting rid of the image per alignment step. At this point, we decided to step down at the micro scale, and we try to tackle the problem that afflict the histopathology images that could lie in different color domains when acquired with different microscopy scanner. In particular, we design a cycle gun-based architecture to learn a bidirectional mapping and try to bring all the images to lie in a common color domain to then ease the subsequent processing task. Our strategy allows to tackle the problem of having unpaired histopathology images during training, as well as being compatible with the RGB image format. So at this point, one could imagine how our end user would be interested in understanding if the image that is seeing is coming from a diseased or healthy tissue. For this reason, I decided also to deploy some classification and segmentation networks. And in this case, as I focus my attention on synchrotron radiation microcity images, which show a very high intra-class and very low inter-class variance that leads even a human with naked eyes to struggle in identifying differences among these images. For this reason, I started building a semi-supervised strategy to segment microstructures that are then employed to with the image classification neural network to let it focus the attention on the most discriminative features inside our images to classify among healthy and osteoporotic images. Our strategy allows us to reach several improvements, both during segmentation and image classification with respect to the state of the art, but also is capable of being aware in detecting fine-grained microstructure differences among fine-grained images. So building upon this work, I decided to dive even more into the classification step. And I also tried to solve the hidden stratification issue that leads microscale image that usually have a label that is assigned at the macro scale to be instead characterized by different subclasses at the macro scale. For this reason, I built a convolutional autoencoder k-mean based clustering approach that is able to derive macro to micro scale information matching. And by manipulating the embedded space, I derived the data-driven weights for the classification loss function, as well as data-driven majority voting threshold for the majority voting whole slide image classification. Our strategy allowed to improve the performance reached from the previous work, as well as reaching up to 28% of per class average accuracy from the standard threshold, the image classification counterpart. So during this last year, I've also moved the first step into the multimodal integration, focusing my attention on the microscale dimensionality. In particular, I tried to exploit the intra-domain semantic knowledge that come from training a large histopathology dataset to perform microstructure segmentation in low data regime. In particular, with this strategy, we employ a multimodal transfer learning methodology to predict synchrotron radiation micro-CT mask lacunae in a low data regime, and we were able to reach up to 63 dice similarity coefficient osteocyte and lacunae segmentation, while improving the state of the art with 44 times smaller datasets. For what concerns the next step, I'm planning to both improve the multimodal integration at the macro scale with the multimodal image registration and at the micro scale for the segmentation part, while as the last step to integrate also different scale images. In particular, I want to study the interaction between different scales in real world data settings, which means with unpaired data as well as heterogeneous in modality, or when some modality are missing, to ultimately provide to the end user with a complete image analysis pipeline. So I thank you for your attention, and I'm more than happy to answer to your questions.
Thank you, Isabella. I have few questions, and the first is regarding the identification issue. You mentioned that you have exploited information from the biometric space to derive loss function weights and majority volume threshold for pairwise and whole slide image classification. Can you briefly describe the strategy you have used to derive them?
Okay, yes. So maybe I can go. Okay, here. So starting from the weights for our cross-entropy loss, I try to exploit those correct matches between the subclasses and the superclasses during clustering. In particular, we exploited the two algorithms for clustering, which are the k-means clustering and the Gaussian mixture model clustering algorithm. So exploiting the proportionality between the correct matches with respect to the all prediction from the unsupervised clustering, I try to weight per class the prediction made by our cross-entropy loss. While concerning the majority voting threshold, I've not just exploited those correct prediction coming from the clustering step, but I also exploited the prediction coming from the pairwise image classification. So I made some proportionality between the correct prediction of the pairwise image classification, as well as the ones that in the same time were correct during the super and the subclass matching.
Thank you. I have just another short question. You talk about multimodal integration. So you said that you are improving it at the macro scale and the macro scale levels. Can you give some insight on the approaches that you are targeting?
Okay, yes. For the macro scale, at the macro scale, I'm trying to exploit some loss functions that are able to also tackle the issue of different bit intensity scales between images, in particular exploiting multimodal loss function during the image registration neural network training. While at the micro scale, I'm trying to improve the image segmentation step by employing knowledge distillation strategy. For example, employing prototype knowledge and noise reduction for the feature during